In this video, I'm going to run through how to make a map. Actually, we've made maps many times already, but in this case specifically, how to make a map that includes something like this. So a base map, as we often refer it to. We're going to use Mapbox GL in this video, but the process is really fairly similar, whether you use Mapbox GL or Leaflet or Open Layers. And we're going to actually make three maps. You can see them here. They look exactly the same, but the way they are actually created is quite different. So the first one, we will create a Mapbox.gl kind of native map, but the second two maps, they look a little bit different too. But that's because there are a combination of Mapbox.gl on one end and an overlay or an additional layer created with Florence and the grammar of graphics. So then the question is, how do you sync those two up together? Our starting point here is the Mapbox.gl documentation page. And as you can see here, basically what's happening is that this all that's needed to actually draw this map is quite straightforward. We need to set an access token, apparently. So that's something that you can actually sign up for on the Mapbox website. You make an account and you get this access token, and for most kind of simple usage, that's completely free. And then what we do is we create a new Mapbox.gl map with this function, and we give it a particular ID of a container, another div that's already on the page. And then we set some additional settings. So what's the center of our map and what's zoom level. As I've also written in the course materials, this is sort of an imperative approach to creating maps. So the first question is, how is this compatible with Svelte or another front-end framework? We can make it a little bit more compatible. To do that, we can follow a very similar approach that Rich Harris on the Svelte website in the examples kind of folder has taken. And as you can see here, he has created a few additional components. Here there's map.svelte and mapmarker.svelte. And so instead of writing this kind of using this kind of function syntax where we say new mapbox.gl.map, we can actually use the template syntax that we're familiar with. So we can say create a new map at this latitude and this longitude at this zoom level, and then on it create these map markers. So what I've done is I've created a little bit of a sandbox, and I've basically ported this original approach by Rich Harris to our sandbox. So just to run through this, as always, we have an app.svelte kind of main application file, and then in this case, I've extracted some of the logic, just as in the example on the Svelte website, into separate components. They reside in a component subdirectory. So I have map.svelte and mapmarker.svelte, and then we'll see in a little bit, there's also a map with Florence.svelte. So that creates some, or that has some additional logic. So what we're going to do, obviously this is Singapore. So what we're going to do is we're going to here set some map related variables, specifically the centroid of the map or the center of the map, the zoom level, and standard width and height. Here it's 250 pixels. And then importantly, we load some data. In this case, there are three dorms, A, B, and C, with some coordinates attached to them. As you can see, this is kind of standard GeoJSON structure, which we know the data container can also read and parse. So here we also convert that to data container for use with Florence, but we'll see that in a little bit. I'm going to scroll down a little bit and skip the rest of this logic and actually go to the template syntax. So here we see that kind of similar syntax that was on the Svelte website. We have a map component. We give it a center, a zoom, a width, and a height. And then within it, as children, we create for each dorm feature, we create a map marker, and we give that marker the entire dorm feature, and we also give it some some label. That label actually is used if we click on one of these features, it will display here. Now, how does that actually work? If we go into map.svelte, what we see here is that we uh, we import some Mapbox related kind of logic. That's basically all of the logic of setting up the Mapbox instance here with the right API key. You can actually see that here if you go to mapbox.js in the utilities folder. You can see here my access token and a bunch of other settings. So if you want to do something simpler, you could basically just copy this this pattern. And then what we do, this is really the same syntax as we have in the Mapbox documentation. We create a new Mapbox map. Instead of giving it an identifier of a particular diff, what we do here is we create this reference to container. As you can see, that's actually a variable in our template here. And what we do is we have created this diff in our template syntax, and we have used this bind this syntax to bind the entire diff, so a reference to the entire diff, to this container variable. So that's basically the same logic as we've previously used in vanilla JavaScript to create a reference to a particular DOM element. We almost never need to use that in Svelte because we just use a template syntax, so we don't need to kind of reference a particular DOM element from JavaScript. But here we do need to do that because Mapbox kind of requires us to do that. So that's why we have that container reference right here. And then again, we set some other settings, the center and the zoom level. And that's all we do, except we also have this particular slot syntax here. And that basically, what that does is, and you can read more about this on the Svelte website, that basically means that anything that's inside as a child of my map component, here these map markers, will actually be pushed into this slot and will be displayed accordingly. If we wouldn't have this slot here, then anything that we would type inside of this map would just not be displayed. So basically here we enable a component to also display its children. By default, it does not. These map markers work in a very similar way. They basically create little new Mapbox markers, specifically adding them to our map. And that's the kind of final trick. What we're doing here is we are passing around, if you will, a reference to the actual map via this get context function that looks a little bit cryptic, but basically that's a way for different components to share some type of shared data. In this case, what is actually shared is a reference to the map. So we can access that reference both from the actual marker component as well as the map component, so they can share the same thing. As a side note, what is interesting about this particular map marker component is that, as you can see, it just has the script and there's no actual DOM elements being written in the Svelte syntax. And that's because all the DOM elements that it's creating are using kind of the Mapbox imperative syntax. So we don't actually need to write any more kind of DOM content right here. So that's a little bit how we cheat in a way. So actually this component is constructing the markers in an imperative way, but as an end user, right, when we're in our app.svelte, these markers here are declared in a kind of way that's very familiar to us from constructing Svelte components. So that's our basically a sort of an adaptation of a native Mapbox approach to something that's a little bit more kind of convenient, at least on the front end, within the context of working with Svelte components and Svelte applications. So that's this top one here. Now our next step would be, we've seen we can create these markers, And that's relatively easy if we just want a standard marker. But as you will see if you dive into the Mapbox documentation, to customize these kind of marker layers requires yet another set of logic. So if you would prefer to kind of stick with the grammar of graphics, you could certainly do that as well. So to do that, the trick is what we want to do is we want to create both the original sort of base map and a svelte graphic or a Florence graphic. And we want to make sure the two stay in sync. And that's really the key thing. So we want to make sure that the points line up in the right location as they do here, but also that when we pan the map, and the panning and the zooming is built in Mapbox functionality, that the points stay in the right location, right? So the points actually have to move when we pan and when we zoom. So how do we actually do that? There are two approaches to that. As you can see here, we show both of them. So there's the first approach and there's the second approach. The first approach I've called the naive sync approach. So let's do that first, and then we can do the slightly more smart way. So here, what we do is we no longer use the original map component, but we use the map with Florence component. Now, if we go in there, it looks very similar, and that's because it is. It just has two, well, really just one difference. Basically, these three lines have been added. And what those three lines do is they dispatch events. If you go to the Svelte website, actually, let's have a quick look at that. Let's see, dispatch. There we go. So far, we have used events that are kind of native to the browser. Think about mouse over, click, etc. But the nice thing about Svelte is that we also can define our own events, and we can do that with this process of creating a dispatcher. And basically the way that works is, let's just go back to Visual Studio Code here. All right, we import this create event dispatcher function from Svelte. We use that to create a reference to this. In this case, this function is called dispatch. And then what we can do is whenever we run that function, the first argument to it is the name of the event. So in this case, and we'll talk about why, we have load, pan, and zoom. And those are basically the same as like click and mouse over, etc. So they're event types or event names. And the second argument is the kind of payload, if you will, or the data that comes along with that particular event. So here, all we've done is we've taken the original map component, but we've added three specific events that it will dispatch. The first one is after it has set up the match or the map, it will dispatch a load event, and it will then send along with that dispatch the reference to the map. Second is whenever the render event on the map is executed, which happens whenever the user pans, it will dispatch a pan event, and along with it, it will send the bounds of the map during that pan event. Now this function, map.getBounds, comes straight from the Mapbox GL API reference. So I think if you go and you look under map, then here somewhere there should be, let's see, there it is, get bounds. And we'll talk a little bit more about what this actually does, but as you can read here, this returns the map's geographical bounds. Basically, whenever we pan the map, the bounds or the bounding box of the displayed map is updating. And what we need to do is we need to kind of send that information to Florence so that it can also update the bounds of the point layer that we have created. So we do that for pan, and we do the exact same thing for zoom. Now on the consumer side of things, so if we go to app.svelte, we can see here that we basically listen to these events, and whenever we receive them, we will execute some kind of function, and we'll look at those functions in a little bit. The other arguments, properties on this component are the same as we had previously. So we have center, zoom, width, and height. All right, so that's our map. And then we have a second div with an overlay, and that's where our graphic comes in. You can see here it has the same width and height because we want to make sure that they match up. But instead of using this map marker thing, we use a basic Florence point marker, and that all looks pretty standard. The trick is basically going to be adjusting, in this case, the scales, the geoscales, which are basically the scale X and scale Y domains. Every time we pan a map, we need to adjust those. So let's actually see how that works. Here we use my geoscale, so we should be able to find that somewhere. So here we initialize it, but it's still empty. But then here we have a function that's called set scales naive. And what that does is it gets the from event.detail, and event.detail within this Svelte context is the actual payload of the event. It will get the map instance, and it will use that subsequently to get the bounds of the map and do some other things with it. So let's look at this function. When does this function actually get executed? It gets executed on load. Now remember, on load will send with it, along with the actual event, the payload will be a reference to the map itself, and that's the kind of the Mapbox map object. It has a bunch of functions available to us. So that's what we're using here as well, because we use this map instance.getBounds. Now we don't just use the getBounds, but we do something else with it. And that's here, this function is called project bounding box. This function actually is imported here from some utility functions that I've provided. Basically, the key issue here is this. Many of these libraries like Leaflet and Mapbox.gl, etc., they work with coordinates in WGS84. As you can see here, basically latitude and longitude, they're unprojected. That means that they are still coordinates on the three-dimensional globe, but under the hood, they actually do have a projection. They just don't really show that projection. In this case, I think I included a note here. In this case, under the hood, Mapbox.gl will project to a projection that's called Web Mercator. And we need to do something similar. So basically, whenever we get the bounds of the map instance, they're not the actual real bounds. We can see that if we, let's just console log this so we can, there we go. Here we get this console log of the map bounds, and what we see here is that these map bounds, well, they're kind of in a weird format coming straight from Mapbox. They show us the southwest corner and the northeast corner, and here you can see they're in longitude, latitude. But those are not the actual map bounds. They're not the actual map bounds of what we see here, but they're again sort of translated back to the three-dimensional globe coordinates. But we want the two-dimensional projected coordinates. To do that, we use this function project bounding box, and we then use the result of that to feed into our traditional geoscales creation function. Now, if we go and we have a look at this project bounding box function, we can see that here in the utilities. Basically, what it's doing is first it will kind of reconfigure the structure of the bounding box, because here it's a southwest northeast kind of thing. Within the Svelte or the Florence context, we like this format where we have just X and Y, and then X and Y basically are an array of the minimum and the maximum for X, and an array for the minimum and the maximum of Y. So that's what we do first. And then after that, we project the coordinates from latitude, longitude to this Mercator projection. So that's what these other functions do here. And again, this is just a little bit of logic that's required because Not all libraries basically operate according to the same approach or the same perspective. So here we just kind of sync these things up. So after we've done this projection step, we can create our geoscale, and that's the geoscale that we give here as well. So that sets up the initial map display, and it will create these points in the right location. But as we can see, when we pan, the points stay in the right location. And that's because whenever we pan, we execute this update bounds function. And that happens here. And all we do during the update bounds, we get from our event payload the bounding box, we project it into the right coordinate system, and then we just update the geoscale. And that will change the max min, basically the domain of our Florence visualization to match again the max min or the bounds of our Mapbox GL base layer. And that's all that's required basically to keep these things in sync with panning and also with zooming to specific points. Now, there's one downside of this whole approach, and that's basically that every time we do that, every time we pan, we will set new scales on the section, and that means that everything will need to be recalculated. Specifically, if you have a lot of points, that's a potentially expensive procedure because all of the points will need to be basically reprojected and re-indexed, etc. So if you have a lot of points, you'll notice that you start noticing a lag basically when you're panning and dragging. So to alleviate that, Florence also has this kind of concept of zooming and panning built in. If you have perused the documentation, you might have found some references to that. So in the local coordinates section, there's a section on zooming, and basically how zooming works is we basically give kind of an object that defines the zoom that the section should take. And it looks kind of cryptic. It's basically an object with 4 keys, X, Y, KX, and KY. And basically that's the offset that the section should take from its original position. So X and Y are the X offsets, so that's basically panning. And then KX and KY are the zoom factor. So the larger that zoom factor is, the more zoomed in we are, and the smaller it is, or if it's negative, then we're zooming out. And we can use this to do zooming and panning on kind of basic graphs like this here in the zoom pan example. So we can set that up even without base map. But we can use the same logic here to do this together with the base map. The whole advantage of this is that basically this way of zooming and panning with this zoom identity property is a lot cheaper to calculate, so it will be a lot more performant with more data points. So how do we do that? It's just a slight variation on our previous approach. Here, what we see is I've changed the geoscale to this my geoscale init, and as we can see here, that geoscale init, let's see, gets originally created here, and then the only place it actually gets changed is in this original kind of setting up the scales function. So what we do there, and that's, yeah, sorry for all the scrolling, that is on load, as we previously executed this function set scales naive. Here we execute a function that's called set scales zoom. And in that function, we do a few things. We set our geoscales, we just call it init now. And then we also store in this variable original bounding box, the bounding box at initialization. So that is the kind of original point, the point of departure, if you will, before any zooming, before any panning has taken place. And we also, based on the initial geoscales, we also store a reference to the scale X and scale Y. Now, whenever we have a zoom event or a pan event, we, let's see here, we execute this function, update zoom. And what that does is all it does is it executes yet another function called calculate zoom identity, and it takes three arguments: the original bounding box, the new bounding box, so after pan or after zoom, and a reference to the zoom identity variable. Now we have initialized this zoom identity a little bit earlier here. When we started, we kind of had its neutral position, so no offset for x and y, so those are both 0. And then the zoom factor is 1, so basically no zoom. Now what's going to happen when we're actually panning or zooming? We are going to calculate a delta x and a delta y. Basically, when we're panning, the bounds are going to be updated, and we're comparing them with the original bounds, as you can see here. We basically take the original top left position and compare it with the new top left position, and just calculate how many pixels is there in between. That's going to be our delta x. And then we do the same for y. And then importantly, we also compare the size, the total width of our bounding box in the projected coordinate system with our new one. So basically, if our original one was, let's say, 10,000 meters, and our new one is 5,000 meters wide, that means that we have zoomed by a factor 2, right? So that's what you can see here. We take the original width, so that's 10,000 meters, and the new width, let's say 5,000 meters, and we divide one over the other. So this will, in this case, return 2. And we use that information to construct this new zoom identity in the format that Florence requires it. And then we store that to our zoom identity variable here. And that's what we then ultimately give to the graphic as well. So in this case, the big difference between these two approaches is that in the original approach, I'm continuously updating my scales, while in the second approach, I only set my scales once, and then after that, all I'm changing is the zoom identity. So as I said, that's a little bit of a cheaper procedure, so it will be much more snappy and performant. The other thing you might have noticed is what is nice is that so I can still use kind of the original Mapbox functionality, so I can pan and I can zoom, but I can also, as you can see here, you see these console logs popping up here, and that's because I've just to show you this, I've set a Florence interaction event, in this case a mouse over event. So you can actually combine these two together if you want.